Hey everyone, so in this video we're going to continue with the last part from the general performance theory climb segment, and we're going to talk about the climb speed calculations. So as we saw, the two most important parameters for us during the climb is going to be the angle of climb and the rate of climb. So the angle of climb showed us the angle of the flight path relative to the local horizontal, and the rate of climb showed us the vertical component of the true airspeed. Okay, and we saw that there was a speed for best angle of climb, which was the Vx, and there was a speed for best rate of climb, which was Vy. And we also looked at the different influencing factors and how they affect the Vx and the Vy. And we said that, generally speaking, the Vx is going to be less than the Vy. Okay, but we haven't mentioned really how and why we use these speeds. Okay, so let me give you an example. Let me tell you that, we had an airport and we have a nice old runway, and we want to take off from this runway in this direction, and we have like a chimney, like an industrial chimney in the way of our flight path, right? And this chimney is like really close to the flight path angle, or really close to the runway. Okay, so brake release point, I achieve liftoff. Okay, so you're at this point, you lifted off from the ground, and you visually spot this obstacle basically. So what speed would you choose for your climb? Right, so the speed which gives you the best angle of climb, or the speed which gives you the best rate of climb. Of course, I'm gonna leave you guys some time here to think. So the right answer in this scenario, of course, is you want from this point, of course, the best angle of climb, right? Because the best angle, what it achieves, best angle means that the highest angle, that this gamma angle is going to be the highest, and what that achieves vertically over the obstacle is actually from this point, from the highest point of the obstacle, is that I'm going to have a nice large separation, a large nice distance, right? If I choose any other speed than Vx, what's going to happen to my flight path, right? So just remember the how we got Vx, the best angle of climb. Let's look at the jet. Right, it was very convenient. So for the jet, it was calibrated speed. We had the thrust and we had the drag. Just quickly sketch them up. Thrust looked like this. Drag looked like this, and we were looking for the maximum excess thrust, right? And so where we achieved it was the VMD for the jet. Okay, so what happens, so this was the Vx for the jet. Okay, so what happens with the flight path angle if I fly with any other speed than Vx? What happens if I choose a lower speed, like right here? In that case, it's visible, so a lower speed. It's visible that the excess thrust is going to be less, so therefore your angle is going to be shallower than the initial one, right? So this is with a V which is less than Vx. Okay, so what happens if I choose a higher speed? I choose a higher speed than Vx. In that case, it's also visible that my excess thrust is yet again smaller, so my flight path angle is going to be smaller as well, so this V is larger than Vx. And again, we see a reduction in the flight path angle, so therefore this obstacle clearance, right, so the vertical distance between the highest point of the obstacle and the flight path is going to reduce. So it's visible that I get the best obstacle separation with using the Vx, so the speed for the best angle of climb. And just for your information, something interesting, in the Airbus family, this is what they call maintaining the so-called green dot speed. So maintaining the so-called green dot speed will achieve the VMD, and therefore the best, the speed for the best angle of climb, so the speed which achieves the largest obstacle clearance. So generally speaking, this Vx would be used to achieve the best angle of climb, the best gradient, and therefore usually in the initial stages of the flight, where you want to achieve a better obstacle clearance, right? So, or maybe after an aborted approach or aborted landing. So this is what you would use it for. Okay, so then there's the slightly higher speed, the Vy. And what the Vi did was the largest sort of rate of climb. So what the difference is between these two is that let's have the same example. So I have here the field, I have the runway, and I'm gonna have an obstacle. Nice chimney. Okay, so what's the difference between these two? So initially I take off, I have liftoff, I reach my screen height, and this is where it all begins. Okay, so let's presume that my initial flight path was maintained with Vx. So from this point, I fly with the best angle, and let's say I fly for T amount. So for a given amount of time with Vx, and this is the point where I get from right here, from the top of the screen height. So from the top of the screen height, I get to this T point flying Vx and achieve gamma max angle. Now let's say after reaching the top of the screen height, I choose Vy. So in this given amount of time, what this does is that I'm going to achieve a shallower angle. However, in this given amount of time, I'm going to get to an altogether, so I'm climbing for the same amount of T time with Vy, and altogether I reach, measured from here, I reach a higher delta Z, or maybe not even from this point, but measured from the top of the screen height. I reach a higher delta Z than I did with climbing with Vx. However, as you can see, my obstacle clearance compared with the top of the obstacle was larger than in case of the Vy. So altogether, in the same amount of time, I climbed higher, so the delta Z max is of course higher than the delta Z, which I managed with the Vx. Sorry, I managed this with the Vy. This I managed with the Vx. So therefore, this one is of course higher than the delta Z in the same amount of time, but also the angle which I achieved with flying with Vx is larger than the angle which I achieved with flying with Vy, and also my obstacle clearance with, let's say, X, so flying with Vx, is larger than the obstacle clearance which I got with flying Vy. So I think this little drawing actually sums up the difference between the two, is that if you fly with Vx in a given amount of time, you're going to get the best angle, right? And with the best angle, you're going to get the best obstacle clearance. However, you won't fly, as far. You won't fly as far with it. So this XX is a smaller distance than this, XY distance. And also your altitude or height which you gain, so the delta Z is less than what you would gain with the with the Vy. And the contrast is true. So if you're climbing with the Vy, you're going to achieve a shallower angle, and with that a smaller obstacle clearance from the obstacle. However, in the same amount of time, you're going to achieve a higher height gain, and you're going to also progress further. So this is the reason why the pilots will use Vy when the quickest climb to the cruise height is required, right? So it also has the advantage of reducing the cruise distance because more distance is covered in the climb. So this one, the Vy, we can say is also the more fuel economic climb. Okay, so usually this one would be called in commercial aviation as flying with minimum cost or climbing with minimum cost or max rate. Okay, because what you achieve with this one is the best rate of climb again. So practically speaking, this is the two kinds of speeds which you want to maintain, and you will find these speeds for any aircraft you will be flying, and it's not just for the jet. The Piper has these speeds published in the pilot operating handbook as well, and you'll be required to know these speeds, and it's very important that you guys understand what these speeds are for, because from my practical experience I see that a lot of students are afraid to climb at a slower speed, for example over a very congested area, where in reality that's what's safest, right? So it would feel natural to want to climb with a faster speed so that the aircraft has more energy, and that's also true that the higher your speed, the higher the safety margin. However, the aircraft's performance might allow you to actually reach higher flight path angle and therefore a higher obstacle clearance. So you need to understand that the aircraft will reach the best sort of obstacle clearance when you fly it at a smaller speed, the Vx. And when you'll be flying the glass cockpit aircrafts, these Vx and Vy actually indicated on the speed tape of the primary flying display, so it's even easier to make these decisions. But to take good advantage of that tool, you first have to sort of understand the underlying basics, and you would use, for example, the Vy at faster speeds when obstacle clearance, for example, is no longer a question. But I often see students climbing even in the glass cockpit aircrafts with sometimes much slower speeds or sometimes much faster than the Vy, when actually you have the speed tape on the primary flight display. So you have your artificial horizon, and here the speed is indicated, and for example you're flying with 90 knots indicated, and here you have for a given speed Vy indicated, and we would be flying continuously faster, or maybe flying continuously slower than the Vy, and it doesn't make sense, right? Because you want to get there as fast as possible to consume the least amount of fuel, and for that you need the Vy, and that's what it's used for. It's not just a random collection of letters is what I'm trying to say, and it's going to be used again even in the general aviation. Okay. So next thing is a bit more Class A aircraft concerned, or more in the worlds of the jet aeroplanes, and it's a bit more interesting. So usually we climb with a constant calibrated airspeed. So for example, we would be climbing with VY, and we would say that is, in reality we've learned that with the change in the pressure altitude, that's also going to change. But in most cases, the pilot would be climbing with a constant calibrated airspeed. So for example, let's say, we're going to be climbing with 250 knots calibrated. So this calibrated airspeed is 250 knots. And in that case, actually, let's look at a very interesting effect. This is something we've already talked about a little bit, but let's refresh it. So here we're going to have the pressure altitude, and on this axis we're going to have basically speed. Okay, so let's say that we're maintaining a constant calibrated airspeed as we're climbing, so 250 knots. Okay, so if my calibrated airspeed is constant, how will my true airspeed change? Okay, so if my calibrated airspeed is a constant, with the increase of pressure altitude, we know that my true airspeed would be continuously increasing, right? We know this, just to refresh, we know that in cruise flying condition, the lift that I generate in the steady cruise condition, the lift that I generate on the aircraft has to equal the weight of the aircraft, and of course I have thrust and drag as well. So thrust would have to equal the drag, but more importantly, lift has to equal the weight, right? So lift would be the lift coefficient times the dynamic pressure times the surface, and this would have to be equal the weight, so therefore a constant, okay, throughout a cruising condition. So we're going to presume that the lift coefficient and the surface area are going to be a constant. So if that is a constant and if the weight is constant, then therefore the dynamic pressure has to be constant as well, right? And here we had the dynamic pressure expressed with two forms. So is the density at the mean sea level in the international standard atmosphere times the V calibrated airspeed squared equals, or it has to equal because it's a constant, the actual density over 2 times the true airspeed, right? And if I want to express from this whole thing the true airspeed, so of course the over 2 goes away, so the true airspeed would be equal to the rho 0 over rho h squared times the calibrated speed, right? So what we can see is that at sea level the rho h is equal to the rho 0, and therefore the rho 0 over rho h is 1. So therefore the true airspeed is equal to the calibrated airspeed. However, as pressure altitude starts to increase, the density starts to decrease, so therefore the rho 0 over rho h under the square root would start to increase, right? Because the denominator starts decreasing, so therefore the entire expression starts increasing. And so if the calibrated airspeed is a constant, Therefore, from this expression, if this what we called is the 1 over the relative density, 1 over relative density is increasing, the true airspeed is going to increase as well, right? Because we said that the calibrated airspeed was constant. And so this is what we're seeing right here, is that with the increase of the pressure altitude and with the constant calibrated airspeed, the true airspeed is gonna increase. Okay, so what happens with the Mach number? So Mach number by definition is the true airspeed over with the local speed of sound. So is the VTES over, if we wanted to express it, the square root of kappa times R times the temperature, usually expressed in Kelvin, right? So what we can see is that as the pressure altitude increases, temperature decreases, and if the calibrated airspeed is constant, then the true airspeed increases. So the true airspeed increases and the temperature decreases. So then we can presume that the kappa and the R, this is a gas constant, so these, both of them are constant. So therefore the entire denominator is going to be decreasing and the true airspeed is increasing, which leads from the entire Mach number to be continuously increasing as the pressure altitude is increasing, right? So what you get is that the Mach number with the increasing pressure altitude is increasing. And so we've already talked a little bit about the critical Mach number and what happens at the transonic speed range. You've also covered this, with fairly detailed in Principles of Flight, but usually there is this critical Mach number where the first part of the aircraft's fuselage, usually the thickest part of the airfoil, reaches the local speed of sound. And so usually that's expressed in the true airspeed of the undisturbed airflow over with the local speed of sound. So it's for the Mach number, you could say, for the whole aircraft. So therefore this critical Mach number is usually less than 1. For commercial airliners, 0.8 below and below 0.9 is usual critical Mach number, and you want to keep your basically buffer from this speed, right? Because after that, in the transonic range, if you increase your Mach number, then you're going to reach the high speed Mach buffer. So basically your lift is going to suddenly decrease and your drag is going to suddenly increase, and there's all sorts of aerodynamic transitions going through, which are very, very negative from our perspective. So we want to keep the speed at or below that. So usually we're going to have a maximum operating Mach number to basically give us an operating limit. So maximum operating Mach number. And so how this looks to keep our margin during the climb from this maximum operating Mach number, how it looks like is the following. So we have the pressure altitude and we have the speed. And so let's say we're climbing, I'm going to use the same example as in the Path Pilot book. So we're climbing with the constant calibrated speed of 240. And so 240 calibrated airspeed, 240 knots. Okay, and as I'm climbing, I'm gonna have an increasing Mach number. And I also have a limitation right here for the Mach number, which is going to be, let's say, 0.76. So maximum operating Mach number. So maximum operating Mach number for our example is going to be 0.78 Mach number. And this is not maintaining a standard Mach number or a constant Mach number. This is a limitation. So this line is a limitation, not maintaining a constant Mach number. Right, so initially, as I'm climbing with 240 knots through the different stages, let's say right here, at the lower altitude, 240 knots indicated is, let's say, a Mach number of 0.72. And let's say here in the middle, still constant calibrated speed would be 240 knots. So therefore here, let's say that would be 0.73. And let's say that here I reach Mach 0.74. And this is what they call a so-called climb schedule. And this is how it's given to the pilots. And this is what's going to be important, climb schedule. In this example, it would be 240 knots and 0.74 Mach number. And because you can clearly see here that if I continue the climb with a constant calibrated speed, my Mach number would increase and eventually I would reach and overshoot the maximum operating Mach number. So instead, they give me this limitation or this climb schedule. They give me this climb schedule and tell me that at the time when I reach with a calibrated airspeed of 240 knots, Mach 0.74, I should change over to maintaining a constant Mach number instead of the constant calibrated speed, and this is called a change over altitude. This is called a change over altitude. And from this point on, the pilot is maintaining a constant Mach number, and if the Mach number is constant, so you have the Mach number, which is the true airspeed, over with kappa times r times the temperature in Kelvin. And if I wanted to express the true airspeed from this one, it's going to be the Mach number, which is a constant, times the kappa times r times the temperature in Kelvin. Okay, so if the Mach number is a constant and these two guys are a constant, what happens in the international standard atmosphere, in the troposphere, with the temperature when the pressure altitude is increasing? We haven't learned this from meteorology yet, but the temperature is decreasing. So therefore, the true airspeed is also going to be decreasing. And if the true airspeed is decreasing with the increasing altitude, in that case, the calibrated airspeed is also going to decrease, right? So from here on this point, the calibrated airspeed is going to start decreasing. Just 1 second. Jesus. Okay. So the calibrated airspeed is also going to start to increase. So we had 240 knots at this point. Let's say we cross-check them in the middle. So here we still have Mach 0.73, and right here we're going to have, let's say, 230 knots indicated. Let's say at this higher point we're going to have Mach 0.74 still. Sorry, this one was 0.74. Just very, very quick correction. And this one would be calibrated 220 knots, let's say. Right, so I hope this makes sense. So yet again, just to recap, and I'm going to give you guys another example on this one. So how it looks like is that initially at lower altitudes, we're usually flying the aircraft with a constant calibrated airspeed. So you have an airspeed indicator where it's shown to you that you need to maintain 240 knots, right? And you also have a Mach meter, which is indicating to you the Mach number, and so it's going to be continuously increasing. And the climb schedule isn't given to you, or the changeover altitude isn't given to you with a specific altitude, because we're going to see that this changeover altitude is not a constant altitude. So it's not, you know, like 10,000 feet, but you know, it can be different based on the calibrated airspeed and the Mach number which you want to maintain. So so it's given to the pilot as a format of calibrated airspeed and Mach number. And so in this case, they tell us that you need to climb with a calibrated airspeed of 240 knots, and the changeover altitude needs to be reached when you reach a Mach number of 0.474 Mach number, and you need to maintain 0.74 Mach number after that. So you're climbing, maintaining 240 knots, and the Mach number is going to be continuously increasing until it reaches 0.74 Mach number, where you go from maintaining a constant calibrated airspeed to maintaining a constant Mach number. And so therefore you're keep climbing, looking at the Mach meter, maintaining 0.74, and the airspeed indicator is going to indicate to you that your calibrated airspeed is actually decreasing throughout the climb, right? But what's important is that you maintain this buffer from the maximum operating Mach number, which is given to you with regards to the maximum critical Mach number, and also the high speed buffet, basically, which you guys will learn about in Principles of Flight in the high speed aerodynamics. Okay, so what is this changeover altitude dependent on during a climb? For example, the speed, the calibrated airspeed of the climb. So let's have two quick examples with two quick climb schedules. So the first climb schedule that we're going to get is the same one as before. So 240 knots. So we know that this is the calibrated airspeed, and the Mach number is 0.74. Of course, this is Mach number. This is the first climb schedule that we get, and the second one is going to be 250 knots, so 10 knots higher, and calibrated airspeed. Okay, and the Mach number, you know, is the same. So you guys can see this example in the Path Pilot book as well. I'm using the same example. Okay, so let's draw, or let's plot the first climb schedule. Okay, so with the increase of pressure altitude, and I'll try to draw like the same size coordinate systems. Actually, what I'll do is just simply put this one over here. Oh, perfect. Work smart, not hard. Okay, so here I'm climbing with a constant calibrated airspeed of 240. So I began from 240 knots, and my calibrated speed is, or sorry, my Mach number is increasing. And the Mach number, the initial one, would be 0.72, and I continue to climb, and at this point it would be 0.73. Sorry, I messed up. 0.73. And this one is still 240 knots, and at this point is still 240 knots, and we reach at this point the Mach 0.74. Okay, so at this point what I'm gonna get, because with the constant calibrated airspeed of 240 knots I have reached the 0.74 Mach number, I'm going to go over or change over to maintaining a constant Mach number. So from this point, I'm climbing with Mach 0.74. And what happens to my calibrated airspeed, of course, is it's going to start to decrease. So at this point, this would be maybe 230 knots. And at this higher point is going to be, let's say, still 0.74, and the true airspeed at this point is 220 knots. Okay, so what happens, and this was the change over altitude, this one. Okay, so what happens if my true airspeed is, like, somewhere here we had the 240, so let's say 250 begins somewhere around here. So I start to climb with 250 and 250 knots. So I begin with the Mach number from, let's say, 0.73. And at the next stage, I'm still maintaining 250 knots calibrated, and the Mach number I reach 0.74 at this point. So I've already reached my Mach number which I needed to reach, so I go from maintaining the 250 knots calibrated to the 0.74 Mach number. So therefore I continue to climb with a constant calibrated Mach number, and therefore, so I change over to maintaining a constant Mach number. So the calibrated speed is going to start to decrease, and it's going to go down to 40 knots, to 30, for example, and 220 knots, and here the Mach number is going to be 0.74, 0.74, 0.74, all the way. Right, so what I can see is that this change over altitude has reduced, so I reach my change over altitude, the same Mach number, at a lower pressure altitude than initial. Right, so this is what I can see. Right, and that's the effect of basically the calibrated airspeed, or the amount of calibrated airspeed on the change over altitude. So you saw that, or you see that we increased the calibrated airspeed by 10 knots, and that basically brought down our change over altitude, and this works vice versa. So if I said, I would reduce compared to the initial one, so this one, the calibrated airspeed to 230, so I lowered it, and the Mach number would stay the same. Of course, the change over altitude would increase in that case, and it also works with changing the Mach number, right? So if I had 240 like in the initial case, like I have 240, but I increased the Mach number, the changeover Mach number to, let's say, 0.75. What happens in that case is that I can still increase with constant calibrated airspeed my Mach number, and I reach the 0.75 at a later point, so therefore my changeover altitude would be higher, right? So, and of course, if I would reduce it to 0.73, for example, I would reach the 0.73 from here. I would maintain constant Mach number from there, calibrated airspeed would reduce, and the changeover altitude would reduce to this one, right? So you can see that this changeover altitude is like not a fixed value for the aeroplane. It depends on the Mach number you want to achieve, and it depends on the calibrated airspeed with which you want to climb, right? So the calibrated speed with which you're going to climb, it would make sense at this point for you to say that, well, you know, initially is going to be Vx, and then after that we're going to switch over to Vy. Or if we don't have a significant obstacle, we'll just accelerate to Vy straight away, and then we'll just climb with that, because we said that that's the most fuel efficient climbing, right? Because that's what's going to give you the highest rate of climb. Interestingly, this was the case only if there weren't any other costs associated with time. And here's where the cost index, another very important definition, comes in. The cost index, right? So airplanes or aviation doesn't only have like the fuel cost. Well, fuel cost is very important, but of course we say that there are some time-based costs of the aircraft as well. So what we say by that is that you can think of it two ways. Like, why do people choose air travel? Why don't people go with the train, for example? The reason for that a lot of the times is because, you know, you can save time, and essentially time is money, right? So time is also going to have a cost. So the faster you can get there, the better. That's one thing. Like you know, traveling faster is more you know, it looks better. It's basically more appealing to the flying crowds. But not only that, but also you're going to have operating costs. So operating costs of the aircraft, which are based on the time it's flying. For example, you know, maintenance costs very often are based on the cycle of the aircraft, on the number of flown hours. You pay the so maintenance cost. You know, if you lease the aircraft, maybe that's also for a given amount of time. So if you lease the aircraft for, let's say, 1 week, for example, anytime the aircraft is not in the air, it's not going to be making money, right? So you want the aircraft to be flying as much as fast as possible, and to basically get from A to B as fast as possible to be generating more revenue. So of course you have you know, maybe leasing, and you also have crew costs, right? So maybe sometimes flight crew, the cabin crew are paid in hourly dues, right? So in that case, you also have other costs associated with operation. And here's where you have the sort of definition of the cost index. So cost index is basically the ratio of the time-related cost of an airplane operation and the fuel and the cost of fuel, basically. So the value of the CI reflects the cost index, reflects the relative effects of fuel costs and overall trip costs as compared to time-related direct operating costs. So in an equation, So CI is, so the time cost, which is approximately measured in, for example, euros per hour. And let's just move this a bit lower so it makes sense, like this. And in the denominator you have the fuel cost, which is also, which can be euro per pound, right? And well, the denominator in this sense, of course, would only make sense if you did the fuel cost calculation with the hourly consumption. So in reality, this would be calculated for euros per hour. So in reality, if you do the dimensional analysis in this form, it doesn't make sense, but this is how it's in the official Boeing website, for example, on how they calculate fuel costs. So I'm just going to leave it at that because I think it makes enough sense for us to understand the importance of fuel cost or cost index. So basically, if you have a zero cost index, what that means, or if you have a very low, let's say a very low cost index, if the cost index is low, it means that the time cost is low and the fuel cost is high relatively, right? So these are relative values to each other. And so it means altogether that the fuel is very expensive. So in that case, and this CI, I haven't mentioned that, or this cost index is given by the company to the flight crews, so the pilots operating the aircraft, and they will just input this number into the FMC, which is the flight management computer. So they will just input this number into the flight management computer, and it's going to help, knowing the performance data of the aircraft is going to help with calculating the best economical climb speed, right? Or the calibrated airspeed and the Mach number, which you're going to need to maintain during the climb. Because in that case, if the fuel is expensive and time is not so much, and so therefore if the cost index is low, what that does is that it's going to result in the maximum range speed, how they call it operationally, and this is how it's written in the Boeing manual, and the minimum trip fuel. So maximum range speed, which was the maximum range speed? How did we call that one? It was the VY, right? It's the VY. The aircraft or the performance data, so the FMC knows the VY for that aircraft, for the mass loading and everything, so it's going to be trying to get as close as possible to the VY. It's going to basically it's going to be flying for a longer amount of time, but essentially it's going to be costing less, right? So it's going to be burning less fuel. If the cost index, however, is high, what that means that relatively speaking, the time costs are high and the fuel costs are relatively low. So the fuel cost, developing a little bit of dysgraphia here. So fuel cost is relatively low. So what that means is that you have maintenance cost and crew cost and leasing cost, which is relatively high, and you're going to have fuel cost, which is relatively low. So in that case, it doesn't matter whether you're that fuel efficient or not. However, it matters for you to be on the ground, as roughly speaking, as soon as possible. So in that case, the schedule calls for the maximum flight envelope speed and ignores the cost of fuel. So this is for higher cost index numbers, and in reality, it's going to be in between the two, right? Because it's going to be a relative indexation of the two. So the flight management computer is going to try to balance the time of cost and the fuel cost, and these are like actual operational data. Interestingly speaking, I've heard stories where flight crews, so pilots, if they had, for example, a delay. For example, they have a delay, and as you know, for example, as well, Wizz Air and Ryanair and all these low-cost companies operate a lot of flights with a fairly quick or short turnaround time. And if they develop a delay, that's pretty bad on their other flights. So if you develop a delay in the morning on the first flight, you have 4 flights, one after another. And if you develop a delay on the first flight, that's going to affect your entire day. So in that case, all of the flights are going to be delayed, and that's not really good. So sometimes to save time, in some cases, you take off delayed, and at this point, flight crews deliberately sometimes increase the cost index. So what this does is that it makes it seem to the flight computer as the time cost is larger than the fuel cost. And practically speaking, it is at that moment, because time costs a lot of money at that point, if you think about it, because you might miss your slot, the aircraft might be grounded, you might miss your, your next slot. Basically, you need to, pay for the ground power unit on the ground. You might need to pay for catering. You might need to pay for, refund the passenger. So time cost at that moment is very high. So fuel cost is relatively low at that moment. So flight crews would increase the cost index in the flight management computer to basically try to make up on the initial delay in the morning and to save some time on the upcoming flights. And if you do that enough, and if there's no delay, it's possible that you can, till the end of the day, you can even and you get some directs, you can even basically diminish your delay by the end of the day. To be frank with you, I don't know, I'm not saying legal, but how accepted this is as a company practice, but there's definitely major benefits to this, and I think it's a very visual example of what this cost index can be used and what it is used for in the practical operations for commercial companies. Okay, so this is where I'll leave it for this video. We're going to continue talking about the climb gradient calculations, which is very important. Because there's quite a few of them in the exams as well. So stay tuned, and thank you for your attention.